And now let's go over the second art for our concept explanation for neural network structures. Now this time we'll be going over activation functions and optimization algorithms. And we're just giving an overview for the most common ones actually used for deep learning model development. So to start with activation functions, the most common ones are typically going to be sigmoid, the hyperbolic tangent function, the rectified linear unit or ReLU, the leaky ReLU, and or softmax. And I have the following acronym down here for memorization, STRL-RS. To be able to go off, you can make any type of acronym you want to be able to memorize, but this is just a brief overview, and we'll be going further in depth for each activation function. And to start, the first one to explain will be the sigmoid function. Now, the sigmoid function, also known as the logistic function, produces an S-shaped curve. Let's get rid of these. So this sigmoid function, or sigmoid functions in general, is a logistic function. And it takes any real value number and maps it in a range between 0, that we have over here, and 1. But not exactly to the boundaries of 0, 1, just for context. This characteristic is useful when the function is used to model the probability in binary classification. So great for binary classification. At high positive values of x, so on the x-axis that we have over here, as the sigmoid function produces more positive values, the function approaches 1. We see on the y-axis, as it goes up and up and up and up, it's going to get closer to 1, and this indicates a high probability of the positive binary classification, so high probability of positive classification. Let me just make this really quick. High probability of positive classification. Conversely, as the x is approaching a higher or lower negative value, such as -5, -10, -100, this would represent the high probability of a negative probability in binary classification. So negative probability of classification. Since we already noticed that the value, the y value, is approaching closer and closer to 0, as we have more negative values in the x-axis, conversely with the higher probability, as there are more positive numbers. We notice this correlation over here. And the function's output can be interpreted as a probability because for any given input value of x, the output value is between 0 and 1. And the total sum across multiple sigmoid functions can be normalized to sum up to 1. So, classification between 0 and 1. And to give a breakdown for each of the following symbols for the sigmoid function, I'm going to use a different color. So we have the sigmoid function over here. And then we have x, which represents our input. Then we have Euler's number as well. So sigmoid x is our input, and E is going to be Euler's number. Which is roughly 2.71828. Let me just zoom out of here. There we go. And then feel free to take a screenshot of this part, and we'll be focusing on the hyperbolic tangent function. Now, to go over the hyperbolic tangent function, the hyperbolic tangent function outputs values in a range from -1 to 1, as we see over here, making it zero-centered, which can help with the convergence during the training of neural networks, which means reducing the chances of error between the different outputs during the training process. So, it helps with convergence, reducing the error during training, for neural networks. And this function behaves much like the sigmoid function when x is near 0, as we see with the S-curve. But as x moves away from 0, the hyperbolic tan function approaches to -1, as we see for negative values, and 1 for positive values, more sharply than the sigmoid. This steeper gradient can lead to faster learning in the early phases of training, but much like the sigmoid function, the hyperbolic tangent function also suffers from a concept called vanishing gradient. A little side context, may suffer from vanishing gradients. For vanishing gradients, basically have smaller values as they are approaching closer to a specific value that we have on the y-axis, and this could lead to slower learning if the gradients are very small, since during the training process weights and biases are constantly updated throughout the training process, hence the term convergence. And as a result from slower learning, this would actually have not that much of a significant change between the weights and biases, making the training process extremely slow. So, slower training. And also a bias towards recent data. Where vanishing gradients can cause a model to have a short memory, and it fails to propagate learning signals back to the earlier data points in the sequence, and just in those contexts as well. But to be able to go over the formula for the hyperbolic tan function, is that the hyperbolic tan function, typically we have our symbol, tan h of x. Then we have the Euler's number that we already know. So we have E, Euler's number. Then we have x as our input to the function. Hyperbolic tan function. There we go. And overall, much like the sigmoid function, the tan function operates as a unique way to be able to train neural networks as well. So let me just zoom out of here, and feel free to take a screenshot. And moving over to rectified linear unit. Now, the rectified linear unit is perhaps the simplest non-linear activation function used in neural networks. For any positive input, it returns the value directly. So, for any positive input, it returns the value directly. However, for any negative input, it's obviously going to return 0, as we see in this graph over here. This creates a sparse activation pattern, which is computationally efficient and allows the network to easily obtain and operate with a derivative, except for the point at 0 over here, when the function is not differentiable. ReLU units can be more robust to the vanishing gradient problem, especially for deep networks, because the gradient is either 0 for negative inputs or 1 for positive outputs. Great for binary classification, as usual. And 0 for negative inputs. And to go over the symbols, so ReLU, we already know that it's that direct function that we have, but really we just have x as the input, as we already know, and then we already know between 0 and x, between what we already given, so we would have 0, 0 in that case, and we would just get the max between those two values. Now, the leaky rectified linear unit improves upon the idea of the ReLU function by allowing a small non-zero gradient when the unit is not active, less than or equal to 0. So we notice in this negative, right here, it leaves some extra room. So we got some extra room for negative values. As our input. We see the difference over here, so that's ReLU, it's 0, but here, in this case, we have a leaky ReLU to be able to ensure that when there is a negative value, the slight slope ensures that even the dead neurons, those that only output 0 in ReLU, have a chance to update and contribute during the training process. So the reason for the slight slope is to allow negative values / dead neurons to contribute during the training process. As there is always a gradient flowing through them, so that is why in particular. So neurons, I would say all neurons have a gradient flow through them. Now, to give a breakdown of the symbols for the ReLU, for the leaky ReLU, so we already know that x is going to be our given input, if x is greater than 0, and then the following symbol is a small constant. For negative values. Alpha typically is set to very small values as well, such as 0.01 to determine the slope of the function for negative input values, and this can be crucial for maintaining alive neurons in the network. So alpha incorporates all possible alive neurons during the training process. And finally, we have the one and only softmax function. And the softmax function is a generalization of the sigmoid function for multiple classes. So generalization of the sigmoid function for multiple classes. For a given vector of x of real numbers, the softmax function normalizes it to a probability distribution consisting of softmax x of I that we have for a given input. The output is a vector of the same dimensions as x, where each element ranges between 0, as we already know over here, or right over here, that's sigmoid, so we have 0 over here, and then 1. And all the output values add up to 1. This function is widely used for multi-class classification. For multi-class problems where it can be providing the probabilities of different classes for a single input. Probabilities of different classes for a single input, and is typically placed in the final layer of neural network classifiers. Placed in the final layer for neural network classifiers. And to go over the following symbols as well. So the softmax function, we typically have E for Euler's number, and we have x of I, which refers to the ith element of the input vector. And J is the index. J is the index used for the sum of all elements in an input vector. So let me just clean this up for you folks so that way you can see the whole scope over what we're talking about. So just give me 1 second. And so yeah, thank you very much for taking time to watch this. If you found this video helpful, be sure and feel free to please like and subscribe. And if you have any other questions, feel free to put it in the comment section. And as always, take care. Cheers. Bye-bye.